This video will cover hypothesis testing for one proportion. We're going to use an example to go through this. At the beginning of the semester, we conducted a Coke versus Pepsi taste test. Business 205 students have been conducting this experiment for the last several years. A common question that has arisen is whether people really prefer the beverage that they perceive to be their preference. In other words, do their revealed preferences match their perceived preferences? Over the last 3 semesters, I found that 58 out of 95 had a revealed preference that matched their perceived preference. Suppose that we believe that this is better than a random guess. This is where the hypothesis testing comes in. We want to try to prove that people are better than the flip of a coin or a random guess. We're going to test this claim at the 5% level of significance. We should always start by carefully defining the null and alternative hypotheses. The null hypothesis is that we're no better than a random guess. In other words, the proportion of people that will guess correctly is 50% or maybe even worse than the flip of a coin. We believe that the true proportion of people that will guess correctly is something significantly greater than 50%. So that's our alternative hypothesis. We're going to attempt to prove that the true proportion is probably statistically greater than 50%. You should always start by drawing a picture. I know you've heard me say that before, but I'm going to keep saying it. So for our picture, we assume that the null hypothesis is true. In other words, we assume people are no better than a random guess. This hypothesis is a one-tail test, which means we're looking for a proportion that is statistically greater than 50%. We're looking for a proportion that is somewhere up here in the upper tail, inside that last 5% of the distribution, because we're looking for a 5% level of significance. We're going to be using again the sampling distribution because we're looking at a sample proportion and attempting to use that to say something about the population proportion. Remember, for proportions, we always use the z distribution. And we already tested in an earlier video that we can assume that these sample proportions are approximately normally distributed. That's the test that we did where n times p is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5. So what we need to do now is compare a z-score drawn from the data to a z-critical drawn from our norm.s.inv. I'm going to show you how to do this by hand, but I'm also going to show you how to let Minitab do this for you. Remember, the critical value determines the rejection region. So our z-critical value is going to tell us where the cutoff is in number of standard deviations. The z-score comes from the sample data. It tells us how far away from 50% our sample proportion happens to be in a number of standard deviations. So z-critical for this particular problem is the absolute value of norm.s.inv of 5%. You could also do norm.s.inv of 95% since we're looking at the top 5%. Because the distribution is symmetric, it actually doesn't matter. Our z-critical tells us that we need to be 1.645 standard deviations above that 50% in order to reject the null. Anything less than that, and we will not be far enough away to say that humans know their preferences better than the flip of a coin. So the z-score formula is calculated like this. We take our sample proportion, subtract out our hypothesized true proportion, and divide that by the standard error. Again, using that hypothesized true proportion in each of these spots here. So the square root of pi times 1 minus pi over n. In our example, that's 58 divided by 95 minus 0.5. Divide by the square root of 0.5 times 1 minus 0.5, divide by 95. That comes out to be 2.1546 standard deviations. Going back to our picture and being able to make a decision, we're trying to determine if our 58 out of 95 is statistically far away from 50%. Our z-critical value, which is the cutoff here, far enough away that we're willing to reject the null, we're willing to accept the chance that we might be wrong, that's 1.645. Our sample happened to be 58 out of 95, which is 2.1546 standard deviations. Our z-score is out in the tail, beyond our critical value, so we are able to reject the null hypothesis. There is sufficient evidence to conclude that students, or people more broadly, will do better than a random guess at matching their preferences, i.e., greater than 50% will match their perceived to their revealed preferences. We can also calculate this using the p-value approach. So we're going to calculate the probability of getting a sample proportion of 58 out of 95 or more, assuming that 50% is our true proportion. This is really just a norm dist calculation. We'll look for the probability that the sample proportion will be greater than 58 out of 95. That's 1 minus norm dist of 58 out of 95, with 0.5 as the mean, and the standard deviation is really the standard error of the sampling distribution, which is 0.5 times 0.5 divided by 95. Always for norm dist, we do true in the cumulative box. This gives us the probability of only 1.6%. There's only a 1.6% chance that 58 out of 95 or more would match their perceived to revealed preferences if we're only guessing. So we're probably not guessing. Our assumption is likely wrong. Back to our picture, what the p-value does for us is tell us the probability of being 58 out of 95 or more. So this probability is really small. There's only a 1.6% chance that we could get 58 out of 95 if 50% is the true proportion. It's highly unlikely that we could get a sample as good as we got, or even better, but we did get that sample. We know that sample is true. That means our assumption that this distribution centers at 50% is likely false. And in fact, this distribution is probably something that's a bit higher, something where the true proportion is statistically greater than 50%. Since the p-value is less than alpha, we can reject the null hypothesis. There is sufficient evidence that students will do better than a random guess at matching their preferences. Now we can do this in Minitab. In Minitab, you go to Stat, Basic Statistics, 1 Proportion. We've been here before to calculate confidence intervals. We always go to Summarize Data for this unless we have a column of data. That's less likely when we have proportions than when we're looking at something that's about means. So change to Summarize Data. Again, small number goes over top of big number. 58 out of 95, write that like you would write the fraction. Now we're going to check Perform Hypothesis Test and enter in our hypothesized proportion of 50%. Go into the Options box and make sure that you have the correct confidence level. Since we're dealing with a 5% level of significance, our confidence level should be 95%. We need to make sure that our alternative hypothesis has the correct sign. We're attempting to prove that 58 out of 95 is statistically greater than our hypothesized proportion. So we need to have the greater than sign here. Remember, whatever sign is in our HA, that's the sign that should go into this box. And remember, just like when we did confidence intervals, this needs to be changed to normal approximation. Once you've made those changes, click OK again, and we'll get our output. So you can see the z value that we calculated before. We got 2.1546, so 2.15. You can use that 2.15 with your critical value and make your comparison. We also get the same p-value that we got before. Just like when we were working with means, you can also use the confidence interval for this calculation. But you'll notice in this case, it only gives you the lower bound. What you're getting there is the lower bound on the confidence interval. So this confidence interval centers at 58 over 95. We go down a mo, and we get this 0.528. We don't even need to know what the upper bound of the confidence interval is. We're looking to see, does 50% lie inside this confidence interval? Since this lower bound does not come down and scoop in our 50%, in other words, 50% would not be in the confidence interval, we reject the null hypothesis. If 50% is not in the confidence interval, it's highly unlikely that 50% would be the true proportion. So we make the same conclusion that we make with the other methods of calculation. Thank you for watching, and I'll see you again soon.